So, welcome today. My name is Dominik Michel. I'm the head of the consulting and projects team here at Mastermarket. Before being that, during my time as an application engineer, I had the opportunity to realize a couple of service projects for our filtration business area. So I'm pleased to guide you through one of these workflows today. We'll dive deep into Geodict and GeoPy, its options and tools, while keeping a certain workflow in mind. So the official title, the generation of cylindrical pleated structures for the digital optimization of filter flow performance. So following these components, well, what we will cover today is at first some showcase of new features in the modules PleatGeo and Complete Filter of FilterDict. Then an overview of what is new and what is possible with a certain workflow in mind. And the workflow, what we will cover today, is the aforementioned. So the generation of cylindrical pleated structures, the digital simulation of the filter flow performance, and cloud-based automation of parameter optimization. So in the latter, we'll focus on GeoPy, automation, and cloud-based parameter study. After the presentation, we will continue with a hands-on session. I'll show you live how this workflow is done and how quickly you can digitally develop next generation pleat filters. We'll conclude with a Q&A session. But let's first start with the first part with some news on the pleats and complete filter. But first things first, filtration, all about digitalization, enhancement, optimization of filter development on several scales. One software solution to design, simulate, and optimize filters, accelerating development process, fast, efficient, and state of the art, and especially microstructure properties in microscale simulation. So we start on the left with the filter media itself. We need those properties in a larger scale, not yet on the complete filter, but one filter element, being it one layer, one pleat, whatever, a sponge. And then the filter element itself, that's what we will replace in our workflow and encase that in the complete filter, where we will then run our simulation on. On this level, I want to highlight a bit on the complete filter. Having the complete filter in one software solution allows for automation and digital optimization. Here we have the full control on the specification you want to have the main axis with a certain pressure, but a rear axis with a certain flow rate. You can do that now. As of Geodict 2024, all multiple outlets, all outlets can be specified separately. And actually, which is not stated on the slide, the inlets can also be non-axis parallel now. So for example, here we have the cross-flow filtration, sectional backlash tubular membranes, and I actually wanted to show you one video we have already seen actually in the morning. A tubular membrane from the main inlet to the outlet, specifying two additional outlets which require flow through the membrane. We can see the flow field illustration for deeper insight into our complete filter, improving the filter knowledge and behavior. Understanding the filter is key to enhancing its performance. So here we can see that there are different feed inlets, the main outlet, and two for the flow field, which is shown with the small arrows here, can flow through the membranes and out of the outlets then. Then next, oops, that was a bit too much. So another tool in digitalization and automation is actually, well, a simple answer, to get the results faster. So we have improved our memory consumption and the runtime. Here, for example, shown for a complete filter lifetime example. The impact of these speed improvements, better and faster development cycles. We reduce from 12 days to 3 days here in this case, for example. Especially useful for simulation with large number of particles. In our case, the improved handling of our 100 million particle trajectories, and the storage to disk of around 4.5 gigabyte per batch. So quite impressive advantage there. Next, then some highlight on the, well, we had 2 examples on the complete filter. Another topic required for our workflow are pleats. If we want to optimize on pleats, we have to generate them too. And preferably as part of our one software solution. Quite new and interactive, as you can see here, PleatGeo. The module contains generation of pleated structures, being at different diameters, height, radii, multiple layers, and so on. We'll see this in a couple of minutes when we go into the module there. So the question then would be, well, we have PleatGeo. Why do we optimize actually? Well, PleatGeo is the structure generation we need for our workflow. The arguments are more general. We have at first, of course, digitalize. We want to save time, we want to save cost. We have heard that in the morning already a bit. We want to understand the dynamics and the processes, and digitally develop the next generation of filter. And of course, major point here too is to shorten the development cycle significantly. Summarizing a bit on the complete filter too, is here to the highlights on the filter simulation. Of course, we have more than one outlet, intuitive settings of the simulation, hands-on import and visualization in one framework, user-friendly UI, and individual visualization settings, what we will see also when we go through the module in a couple of minutes. Completing the introduction, in general, there are several interesting topics coming up in the filtration area, especially important for our workflow today, covering not only inertia, but turbulences in our flow simulation too. As already advertised, we also want to, we will further develop features for more complex applications or better performance for all our customers. Beginning with the filter media scale, the features of adsorption will be extended to also simulate the desorption of particles. Electrostatics are further driven in the next years with validation towards experiments, as well as to improve and enhance the electrostatic decay functionality. For the coreless sense, we're still working on validation with other systems like fuel, air, and water air to extend our position there. And as I already mentioned, especially important for our workflow today, covering not only inertia, but turbulence by including large eddy simulation equations that we can predict turbulent behavior there. But next, let's jump right into the workflow. And we start with, well, the workflow here titled today, Cloud-Based Pleat Optimization. So as a classical application for this framework is the optimization of pleat count in the filter element. By running simulations, different pleat count, it's possible to digitally find the optimum between the pleat count or the filter area and the pressure drop. But you can think optimization by digital simulation even further. See, for example, the one on the right. We can optimize the design of our filter, can optimize the pleated filter itself, can optimize the casing based on our flow and pressure distribution, or just we can optimize our knowledge about the filter in general, isn't it? In the end, why do we do this? As I already mentioned, significantly reduce the time to market performance through digitalization. So what is the digital workflow here? Or in general, actually. Highlights of the workflow is to optimize an existing filter element, starting with the import of a CAD structure into Geodict. Using PleatGeo, it is possible to generate cylindrical pleated structures with given input parameters to fit in the original CAD filter. With this feature, several structures can be saved with varying parameters, such as pleat count, pleat height, or several porous layers. And in the following, the parametric simulations are performed either on a workstation with Geodic 2023 or improved in user and sorry. It can be either on a workstation sequentially or in parallel using the new cloud computation capabilities, which came shipped with Geodic 2023 and improved in usability in Geodic 2024. By analyzing the results, the best performing configuration can be found and tested digitally. This promising prototype can then be manufactured and validated at the test bench, as you're doing it at the moment, isn't it? This procedure allows to optimize the filtration relevant parameters, saving time, saving material, saving time in the production and testing of additional filter elements. To reiterate that, so we have a classical application of this framework, optimization of a pleat count. And in this plot, just moving right out of the screen at the moment. So at the plot, you see on the x-axis the number of pleats, and the vertical axis the pressure drop. And you can see that with increasing number of pleats, the pressure drop goes down a bit, but increases again when the pleats getting a bit too tight and too packed. We have evaluated this here with several tip ready, but we will see that in a second again. So to produce the filter elements, the minimum of this curve is the goal for a good performing filter. So here, for example, only geometries with 67 or 68 pleats, depending on the possible pleat tip radius, would be produced and taken to the test bench. So, cloud-based workflows have then the advantage to shorten this parametric study significantly. Obviously, because all the cases run in parallel. And of course, you have access to high-performance computers which you don't have at your lab, at your desk, or in the server room. In the summary, means that we have a reduced time to market frame here. And of course, a bit contrary to that, it may motivate you also to run a lot more test cases than you would previously have done or planned. In our case, we'll import the given CAD data, import our CAD structure, and then generate, substitute, and simulate. This can be done in parallel in the cloud. And then collecting all these results, we find the best performing geometry and the promising prototypes, and can then do this at the test bench. Now, let's start with the workflow in detail. Now, the workflow starts with the import of a CAD geometry. So let me guide through the tools, the modules, and highlight some of the aspects of them. If I want to optimize my filter, start with the geometry of the filter. The casing, all the solid parts. On the right-hand side, you can see a first draft of our filter, which we will use today. This is a triangulated geometry generated somewhere in a CAD software, which contains the casing, all the solid parts, and the first draft of our cylindrical pleat. As you can see in Geodic, there's the import GeoCAD module. Let's see if I have a mouse over there. No, kind of find it. Exactly. So if we use that, the import CAD data is already in Geodic. So in this case here, we have one OBJ file consisting of 10 casing and filter components. You can see here, right there, directly feedback that you can see the structure elements of your CAD data. There's not much information on the left side, because that depends on the next information. To import, you can currently import OBJ and STL data with any surfaces you like. Anything can be included, can be several files. And in the next step would include, there is a suggest button. You can specify the unit, and you can specify, you specify the unit of the data in the file. Doesn't need to be imperial, doesn't need to be metric, can even be inch. And then with the suggest button, you have the full control over the structure size. There's actually two possibilities at the moment. One is to give the voxel count. So in this case, for example, if a filter structure has a height of 1 meter, and you're choosing here 1,000 voxels, meaning this is the longest axis, and in this case 1 meter, would result in a voxel length of around 1 millimeter. You may say this already exceeds the size of your filter. So the other option would, of course, be to have, on the other hand, setting the voxel length directly. Then here, for example, 100 micrometers. With my filter of the size of 1 meter, I'll probably have some 10,000 voxels in the longest axis. That is still manageable. Geotic can do that. I wouldn't do this on my laptop actually. But we have your full control of your discretization. You can specify how large your structure will be, and we'll see that in a second when we import that. Some other things here. You already get feedback on the left-hand side. You see the coordinates, the size of the filter. If there are some issues of the input files, we got several input files and they're actually not aligned but stacked. Then you get already this here that my 1 meter filter has a height of 30 centimeters. Something went wrong. You already get that feedback here. You can have directly feedback on the discretization and the sample size. And then you can, if you have we have actually just included two things. We have included the unit of the file, and we've included the size we want to have, and then we can import this thing. Of course, large structures will take a bit of time, but it's not about the complexity of the filter. Of course, this has an effect too, but and complex structures can result in artifacts. But timing is here actually the surfaces we needed to discretize from the CAD format to our voxel-based view. After that, Geotic again gives you feedback. It tells you warnings if it had discovered any issues in several checks it has doing. For example, in water tightness, completeness of the structure, repeating edges, too small triangles for your voxel lengths, any things. So you get direct feedback, and we will see some of those feedback already in the next slides. Some things don't matter. It warns here, for example, that this may have certain repeating edges, but I actually kept some of the artifacts on purpose here. So then from that on, we are back in the Geotic viewer, and for the triangle view, you see your CAD data again. So for example, here you can see let me see if I find my mouse. Yeah, you can see here the filter element has two surfaces. Of course, one inner and outer. Two surfaces determine the filter element, the pleat here. You can see the round openings here. As to be expected, a triangulation of a round circle is quite difficult to have very small triangles here. But you can investigate the triangulation here again on terms of any issues there. So you have direct view on your CAD data. So when we now use that and compare those two, for example, here the surfaces of the filter elements and the round openings here, comparing that now when we switch from the triangle view to the voxel view. So here, for example, we have two discretizations. On the left-hand side, a 400 voxel case, 272 micrometer sampling. This is what this here. You can already see that this discretization is kind of rough here. The tip of the valleys are kind of they are small. They are small by design from the CAD structure, but there are not many voxels in between. While this one here has 1,087 voxels in the vertical. So it's a sampling of 100 micrometers. Well, fun fact, you can see on those values actually what I used as a suggest value, isn't it? Because the even numbers are those I suggested and the other one is calculated. Seems a bit too loud, isn't it? Yeah. So here again, for the level of detail, the 100 micrometer sampling has far more smooth sampling of our pleated structure. Therefore, also more voxels at valley points here. And of course, the circular rounding is here discretized. You can see the discretization effects, while on this one here, the opening is much more smoother. The images which will be contained in this presentation are based on the 100 micrometer sampling. We will later on do the 400 voxel images because we want to have faster results. At this point, of course, you have the compromise between better sampling or a faster result, of course. So in this case here, 100 micrometers could be fine. We can see that later on. Now we have imported our CAD structure. We are now within our voxel-based domain and have imported our first guess of our pleated filter. But at the moment, we have got a lot of structures in there because the input file contained 10 surface structures or recognized 10 structures. So the next step would then be to reassign materials. Here again, you have the complete control of your materials. On the right-hand side, you can see here again the our imported structures. And if you click on structure, you can reassign materials, can reassign the material ID, swap materials, and so on. In this case here, I want to replace the pleat. So the casing can just be one material. Everything which is not the filter itself, I can put to one material. So in this case here, where's my mouse? We have just one casing left here, and the filter element is the green one down there. Actually, I think in the next one is a bit more brighter green. If we are already here, we can set the material of our filter to be a porous medium with oil inside. Okay. That's just because this filter was an oil filter by design. Yeah. Okay. So next step will then be we continue with the reassignment. We have now changed the material IDs. Now also we need to specify some sort of inflow and outflow. The inflow here are several inflow holes actually going through the same circular area down there. The flow will go to the boundary, going down there through the pleated filter into the middle and then up again through this outflow. But, well, I said, okay, this will be the flow direction. For being sure of that, we need to be sure about water tightness. So one thing we always do is to check for the geometry. In our case here, for example, we check for holes. Maybe the sampling being too coarse. Like for example, if we would have sampled that here with 500 micrometers, we probably won't see a lot. And even the filter element wouldn't make it. Then there are also sometimes differences, gaps between geometries. If the CAD structure for the CAD software was fine, but actually the surfaces didn't align properly. In one example, the casing wasn't stable enough, and we had it was easier for the flow to go through holes in the casing instead of through the filter element, which probably wasn't the intended outcome. So the next iteration of the CAD data was better then. The purple one down there is actually just a check for the outer hull surface tightness. If anything goes inside, there will be a hole and our filter would be leaking. In this case, encasing the surrounding proved this not to be the case. There are some small voxels missing there, But as long as the inner and outer surface is completely tight, this doesn't matter if there are small voxels missing there. So double checking on that. We have some easy to use post-processing tools for this voxel manipulation. We can change that. And then we are nearly close to importing finishing the import. If we have not already done that, if we have not already assigned materials, we can set all the material properties, fluid properties, and actually labels too, that we can find them again. Here is the inflow, outflow. We have specified which fluid we will use, which fluid is in the porous medium, and the invisible outer void is still in there. So after setting up all that, the import is completed. We can go to the next step on that. That would then be, well, before optimizing the filter element or the filter casing, for example, improving the understanding, what we need is what are the key performance indicators we actually want to investigate here. One could say, okay, this is pressure drop, but looking at this a bit in detail, pressure drop where? Between the inlet and the outlet, so the first and the last part, or at the filter element itself, what is the pressure drop there? Or maybe the difference between the pressure drop inlet outlet and the pressure drop at a filter element itself. Is there some sort of bottleneck location where actually the major part of the pressure drop is lost? We can check for the behavior along flow trajectories between inlet and outlet. As you can see, there are several possibilities, and we will actually investigate all of them. Of course, some sort of permeability impact is possible here too, but as we are only changing later on the pleat count and not the pleat thickness, that won't be much of importance for our case here now. So you can evaluate all those in Geodict, and we do that with a complete filter simulation with FilterDict. So this is part of the prediction tab. We will focus here on the complete filter and the filter flow experiment. So we don't have the multiple outlets as specified last time, as specified in the highlight section. So there you can set up the full flow experiment. You have the full control about material settings. It's actually here again. You don't need to change the constituent material. If you just want to change the permeability, for example, and you can do that here because then it's a parameter in our flow command and easily to change in the parametric study. Then we have in the middle window the flow set up as a reminder here. For the inlet, you can here change the pressure drop and the flow rate. As I mentioned, for the cross flow filter, you can change all the outlets again here individually, separately from pressure or flow rate. Then there are some solver parameters on the flow solver, gridding, on the stopping criteria and so on, but we don't need to go into detail on that here. In commonly, you can just start that. So use the default settings there. Okay, then after running, we get the result file, which actually can be accessed programmatically, which we will use later on. The pressure drop is highlighted here prominently in the report, but also in the result map. Oh, sorry, I was already there, wasn't I? Okay, maybe I touched the mouse. So the pressure drop is highlighted in the report. Here, it's down there. And in the result map, where it can be accessed as a variable from our optimization script. We'll come back to in a second. What I want to show you here, there's a tab about flow visualization. The flow visualization, you can load the volume fields to inspect the velocity actually the velocity components. There's the X, Y, and Z component here. There's the absolute velocity. There's a pressure field. And all of those are volume fields in GeoDict. And as there are volume fields in GeoDict, you can also access them programmatically. You can view them. And I will show you in a second what you can do with that. Some small illustrations on that. Here, for example, we have the absolute velocity field here in a transparent view on the right side with a transparent view, and especially highlighting all here going through the filter element, and and of course if we have the parameters of our flow field, the X, Y, and Z components, then we can also plot the velocity field with arrows to highlight the direction and the strength of the flow. The gridding has to be regular here in this case, so it's mapping all arrows on top. The same is actually true for the pressure field. We can similarly illustrate that. The highest pressure is, of course, at the inlet, and it drops along the filter element. Let me show you a bit here on the screen. Here you can see the pressure drop. If I slice through that, there are two slices printed here. One is a vertical slice, so you can see same as the velocity file, the velocity field. You can see here the pressure drop going down. Well, this is actually the filter element. And the horizontal slice shows you the inside and outside of our pleated structure. So, as I mentioned, every field in GeoDict can be accessed programmatically and be part of your evaluation workflow if you desire. That actually some analysis functionality is in GeoDict, of course, too. So in this case, we can use compute metrics on volume fields, and I think Andreas Wiegmann has shown one of those in the morning, isn't it? Compute metrics. Here in this case, to calculate the slice-wise minimum and maximum values of our pressure field. In this case, slice-wise in the vertical direction. So starting from the bottom, going up to the top where the inflow was. We have here then, you can see the minimum pressure is always at the inside, the blue area here. And the maximum pressure increases up to the top because that was where the flow was pressed into. So again, here then the maximum pressure, as I mentioned, is pre-pleat, the inflow regime, the minimal pressure post-pleat. Well, actually not exactly. If you just take a slice-wise minimum maximum, it's not that it's at the same position at your filter element. As here, for example, I highlighted this with two arrows that the minimum is the complete blue area and the maximum is actually outside this orange ring. But the purpose on that here would, for example, be if you have a sudden pressure drop somewhere around the vertical, then you can see, okay, yeah, in this case, it's quite simple. But if there's a more complex distribution along the vertical axis, you can see that there's maybe a higher pressure drop, there's a lower pressure drop. And then you can also say, okay, there is a higher maintenance where higher pressure drop is. Therefore, you can already investigate it. You can already investigate the pressure field with the onboard GeoDict modules. So we have not yet done a parametric study, but you have already get the impression on what is happening in your filter. To have a more sophisticated tailored analysis is possible with GeoPy, where we can extract the information we want to need. Actually, there will be a plenum talk tomorrow on GeoPy and GeoApp, what I will be doing. But summarizing a bit on the complete filter, we have the simulation. We have used state-of-the-art solver, and we have used it we can use it for digital optimization. Now, what is missing now is the third part of our workflow is the generation of cylindrical pleat structures, and for that we use PleatGeo. So, yeah, To have the parametric study to investigate the various effects such as pleat count or different pleat geometries, we need to generate a new pleat. As of GEDIC 2023, this can be easily done and is in our model tab under the module pleat geo. So then, first, the shape of that. Well, you have a UI where you can vary all parametric options from the pleat count over the diameters, the radius, the rotation of the complete thing. And what is not shown here, but we will show on later in our live demo, is a direct preview of our pleat shape. This is directly visible. If I change anything there, I get the cross-section of my pleat would directly change on that. This is especially true if I click on the M-shaped. It's possible to have M-shaped pleat, so a long pleat, a small pleat, a longer one, but that's actually not included in our workflow, so we will not use that. Just to file through the other tabs, you have, as I already mentioned, the complete control of what you are designing here. How many layers do you want to use? What is the thickness of each layer? What is the material of each layer? Then, oops, this was the one. Then the complete parameterization is done with adding also the pore space fluid and the voxel length. Actually, the sampling of the whole thing is determined already by the diameter and the voxel length. So in this case here, well, here was some sort of 860 squared times 60 voxels. We'll do a bit different later on. To complete that, the last tab is even possible to export that as an STL format. And you have, in this case, the full control on the quality of your output. So all you've seen here is, so we have generated our pleat structure. It's an easy to use tool. It's ready to implement our result. So how do we integrate that into our previous structure? Well, there are several ways to do that. We have our pleated element. We want to include it into our casing. We can export it as an STL format, and then using again import GeoCAD and choosing the pleated element using these exported data. We could also use GATGeo, our geometry structure, adding the geometry to an existing structure where, of course, we have to place it there. And the third option would then be using GeoPy to replace the current cylindrical pleat by a newly generated one on a voxelized structure basis. At the end, for our parametric study to investigate the various effects such as pleat count or different pleat geometries, it is necessary to automatically incorporate newly generated pleated cylindrical filter elements into our old structure. Therefore, we'll be using GeoPy in a second. Just to summarize a bit on that, we can digitally generate cylindrical pleats. This all is still inside our one software solution, still inside GEODIC. We don't need to import another CAD pleat. And we are actually ready to use automation and parameter study. And that's something where my search and place didn't work. So let's coming to our fourth part on that. It's the automized optimization with GeoPy. So actually, let's go to the final and interesting part of our workflow. So the GeoPy workflow, how shall it look like? What's the workflow for our GeoPy automation here? At first, as I mentioned, to analyze the current geometry, we come in with some first guess of our pleat filter. The tool shall analyze that, shall determine where is the boundary, where is the center, how many pleats, and so on. we extract the modeling parameters from the identified pleated filter. Then we change those generation parameters and generate a new pleat filter out of that. And then, okay, some simple task. We have to add the new filter structure to inside our casing. And with that, we can evaluate the pressure drop for the newly completed filter. It's actually newly completed complete filter. So I don't want to go into detail here on the GeoPy script. We can do that later on in our live demo. So I mentioned GeoPy already. GeoPy is our Python interface for geodict commands and targeting geodict automation. What we have done, what you can see on the right-hand side here is a small UI in the geodict design framework, but actually generated by a Geo app, by a GeoPy script, which I have written here. The analyze functionality needs to know what the pleat material is, needs to know which material ID of our structure is actually the pleat. And then it can analyze that for the, where's my mouse? For the bounding box, for the pleat center. Here, for example, you can see that it detected the pleat between some vertical slices, using some slice as a reference. That's actually the printout on our command line interface. Then it found that the pleat bounding box is somewhere there. It calculated a center point of our pleat, of our volume, where our new pleat shall be, where the old pleat was. Calculated the inner and outer radius out of that. What was the previous one? Because at the moment we don't want to change that, so it needs to get the information. We don't want to give it the information there. And then it said, okay, I counted 50 pleats on that. Then some parameters the small script didn't want to evaluate. For example, the tip radius, the valley radius, the pleat thickness. Probably one with a bit more time, one could also extract those information, but haven't done that here. So we just say here that we want to include those in there, the medium thickness and the inner and outer radius, and replacing that with a certain amount of pleats. And then here, okay, this screen just didn't align a lot, but we can create new pleat with Pleat Geo and replace that in our structure. Doing that, just using that script as it is here, we will say later on see there's actually another section down there which says run simulation too. But we have now the ability to sample all possible values. Well, of course, the pleat count has to be integer, but the outer tip radius here, you can, for example, see that here are 45 pleats, and the same slice going up to 75 pleats. You can see the obvious difference. Between the lower one, this is an 0.65 outer tip radius, 8 millimeters, sorry, to 0.8 millimeter. You can see the difference, but you have to look closer than that. But as I wanted to illustrate here, with this small script, we have the ability to set up any sort of pleated filter inside our pleat geometry. And with that, we have our initial structure. We have our initial structure and a small UI with a couple of features. That's actually what the automation in Geodict is doing, or we'll also talking about tomorrow. So we have the ability to change the pleat structure with a few parameters and run the filtration simulation to extract the pressure drop and the filter area, and generate, also part of the Geodict automation, generate a result file with just the information we want to have. So here, for example, this here contains then the information about how many pleats, what was the pleat count, what was the pleat thickness. So already having in mind that we can run the automation, the parameter study with the pleat thickness as a parameter. Then inner and outer radii, And then we get the pressure drop, and here's the computation time, and of course some additional files which were calculated intermediate, and of course the result file. So we can run this script for one case. We'll do this later on. We could also include a loop inside the script to run several cases. But actually, we want to use the very functionality here to run several options within a per parameter study, not sequentially on our PC, but in the cloud. So, to further increase the productivity and shorten the simulation times for very large parameter studies, the cloud capabilities were from GEDIC 2023 can be used. Has, of course, the advantage that simulations are all performed at the same time, which results in one runtime for all simulations instead of sequentially executing one after another. And highlight here, as of GEDIC 2024, these are included as highlighted buttons for each module, and also the GeoApps included in the UI. We have here next to the run button, we have also the actually run in the cloud and run in the job queue button. We had heard a bit about the job queue in the morning. I will actually show you here on the slides some of the cloud access options. Actually, the run in job queue looks similar. It's just that a job queue doesn't have a lot of resources to start. And of course, on the macros, on the scripts you have done here and there for the automation of what we will use later on, there are the same identical buttons too, that you can directly start anything in the cloud or on any server at your lab or at your office. So our use case. Now, the minimizing the pressure drop, accelerating development cycle, reducing costs. Well, what are our costs here? Is it production, material, personal costs, especially for the assembly, the tests, evaluations? Well, the question would here for you be, there's actually a question for you. What would your costs be? What is the cost of your sample? To produce the filter medium, to pleat the filter, to complete the assembly, to book the test bench, having the time on that, to make the measurements, and then resulting in you need to do that again. And so expect to produce 3 filters before some sort of final is reached. What are your costs on your for this procedure for this sample? The advantage, of course, is to have the automation by digitalization, to have the development cycle completely in the computer, in the virtual space, in our digital material laboratory, which in our case here, which is definitely much faster than the experiments. The main idea of the cloud, as I mentioned, is unrestricted resources. You pay that with paying for the virtual CPU hours, but you get strong resources on demand and not when they are available, you get them immediately. So you have a massive reduction in times. Here, for example, we're reducing from 13 days to just 3 hours. And further, of course, the cheaper than a trial and error. In our case, the computation costs are just some few thousand euros compared to creating, manufacturing, assembling, testing, and so on. Further, of course, you can say that, as I mentioned already, you maybe have more cases than you would do physically. Here, for example, what we'll see here, the time and the costs are depending on the actually 60 different samples we'll do in a second. You probably will say, okay, I won't do that in the lab. But of course you won't. But here you get more cases, you get better cases, you get actually better results than your samples. Of course, it may also be that in a parameter study where if you more than one parameters you want to optimize for, you don't get more. You can have more than one target indicator. The optimum may not be unique. You may have 2 or 3 which are close to the best, all have some optimal concept, but then you still have 2 to 3 samples which you can produce, which are already the best ones you can achieve. So now let's have a look on how these numbers came into be, and how we can start these calculations out of the box with Geodict. So I need to tell you a bit about what the setup here was. The let's say the expert knowledge told us that pleat count should be somewhere between 60 and 75, just to shrink the possible range a bit. And let's say the tip radius is between 0.6 and 0.8. So here we do a 2-step automation. First, the core sampling the pleat count with a number of 3 and 0.05 millimeter sampling in our tip radius. So that would be 30 samples, 6 cross 5, and we'll find the minimum of that. And if we found those minimum, we do a fine research, this time with a pleat sampling of 1 and an 0.01 millimeter sampling. But we'll come back to that in a second. Then here some details for the cloud testing. We ran each simulation on an 80-core machine with 320 gigabyte RAM, and compare that to a normal workstation or a laptop, which would then be first sequential, and second, well, this is just an 8-core machine here, so don't have more power than that. So, but if we want to start that, as I mentioned, we use the very functionality here. This is the parameter window, as you have seen it a couple of seconds ago. Just in this case, I can enter several values here. Those two are linked by the very functionality that we have 1, 2, 3, 4, 5 radii. I just use the inner radius as half of the outer radius for this purpose. And we have the pleat count going from 60 to 75. So this makes 30 test cases. And then, well, actually we can close this parameter window here. If I then click run, it would do the 30 calculations sequentially on my machine. But if I click run in the cloud, it opens up a window where I can specify the CPUs I want to use. Here in this case, I choose the 80-core machine. And after 1.5 hours, I get then here a completely green parameter window. Green means in this case it's successfully completed. There are also some other information. Of course, if the cloud machine is starting up, it's starting your simulation, it's running the simulation, it's finishing the simulation, and this will be also highlighted in yellow in this case. Also some things like I terminated what the question was in the morning. And every line here can be terminated. So then it would be red, but I would have terminated that. So could also be an error that we have chosen a small enough computer, like here, for example, 4-core machine with 16 gigabyte RAM. Most likely the flow simulation won't be running there. So it will tell me after a couple of seconds that I should pick a larger machine. But here in this case, we can see that all 30 calculations have been finished. In this case, of course, we do everything in parallel. The longest running simulation determines the maximum cloud time. So in this case here, we have an acceleration factor comparing to our workstation, our sequential run, which would be around 6.5 days. We have a cloud simulation finished, and as I mentioned, that's the longest running simulation of 90 minutes, which is an acceleration factor of 102. So, of course, question would then be here, what would your time to get a measurement result? Probably not within 1.5 hours, isn't it? And that's already calculating 30 samples here. The simulation results of our core sampling means then here, I have to leave the screen again a bit. Yeah, in that case, you can see the pleat count on the one axis and the tip radius on the second axis. And you can see that for every tip radius, as to be expected, it goes down and then up again when the pleats get too crowded. The same is, of course, here for a higher tip radius. We reach that crowded point earlier. But also can see, this time I use the mouse, that we have some sort of diagonal drop down here. For smaller tip radii, actually goes to higher pleat count because there is more space inside, isn't it? So here in our case, as you can see that we have kind of a rough sampling here. We can choose a location for a finer sampling. This would here then in this case be, let's say, we search again between 69 and 72 pleats, because actually on the edge, there's not much difference between the pressure drop for 69 and the pressure drop for 72 pleats. So we have to search to have a finer sampling on that. Actually, when we have a look at that, that would be an ideal case of a gradient optimization routine and not just the grid sampling we are doing here. But we want to here keep it simple. And I think, a grid sampling we can do in the cloud and gradient optimization we cannot. So we do the same thing for our finer simulation. And in this case, actually highlighted on the left, well, on the middle, you can see again our vary functionality that we have entered different values. Because on the left one, that's a different screen now. That's the here the selected machine is already chosen. You can also specify GDIC versions, licenses, when the whole thing shall stop. That after 3 hours it should be finished. If not something, then just stop the virtual machine. We are paying for that, so we don't want to have it extended. And here all the variations, everything which change, all the 30 cases are stated there. And on the right side, we can see that we have all 30 simulation finished. Everything is green, and we can summarize that. So again here, the acceleration factor, we go down from 6.5 days to 105 minutes. So an acceleration factor of 89 in this case. But the full finer study is done within 1.75 hours. So 105 minutes, that's fine. Let's have a look at that. Here again, we can see a bit more on details. It's actually not, it doesn't seem to be stable on there. It actually gets too fine. The sampling was not the discretization was not fine enough there. But for higher tip radii, we get a minimum here. We can say here, okay, the minimum is at 71 pleats with an 0.59 millimeter tip radius and gives a pressure drop of 54.95 millibar. And actually, I think I missed the parameters telling you that the complete thing here is calculated with an inflow of 10 liters per minute and a filter permeability of 10 to the power minus 11. So summarizing on that, we have done a simple grid approach, sampling the pleat count, actually from 60 to 75, sample the outer tip radius, evaluating the pressure drop versus the pleat count and the tip radius. We have running 230 simulation. You can actually also say, okay, pick half of that. But we have done 60 simulation in 2 runs, which can be done sequentially. Don't need human interaction in between, in less than 3.5 hours for less than 10,000 euros, replacing physical test samples of, well, what would be the cost of that? So summarizing a bit on that. GeoPy and GeoCloud. Automation, simulation, increasing productivity. As I mentioned, we'll highlight a bit on the Lena talk tomorrow morning. Scalability of the simulations through parameter studies and using the cloud functionality for that. And in the end, digitalization of the product development cycle. Let's go to Geodict. So I can browse here again to the workflow data and import my CAD. So as I've described you earlier a bit, that we can see here our 10 materials. And well, now let's suggest, as I mentioned, 400 voxels may be fine, isn't it? So I've included 400 voxels. Now it includes probably that here in the vertical direction, 400 voxels. We have a size of, okay, the filter has a size of a height of 5.5 centimeters. Then I can press import. That you can see here the coordinates. This fits of overlapping material. I think I missed that in the presentation, isn't it? That we have also if it overlaps those surfaces, and we got all the information here, and we are close to being finished in a second. Well, of course, it has to calculate all 10 structures. We have here, for example, we have here the seal gasket, 2 caps, and then should a triangulation be shown? Yeah, that's probably a good idea to have first a look on that. The structure invisible, also a good idea. Okay, well, 400 voxels, that's fine. So now, now here we have our triangulated structure. Let's see, we can also have here, coloring is at the moment the material ID, that's fine. We see the faces. Maybe we want to see the faces and the wireframe. And then can clip, let's see here, that's the x-axis. We clip from top to bottom here, going inside there. We can see here, and what we had seen, our gridding, all the elements. I can also, the visible mesh here is at the moment everything, but I can also exclude some parts of that. Maybe, for example, the solid outer part. The 8 is, well, case bottom assembly, okay. Then the 7, yeah, that was the inner one here. Can also remove everything but the pleat. Okay, there are some structures up there too. Oops, I think 2 was the wrong one here. So, can go there, and we see here our triangulated pleat. But we wanted to have a look on the structure instead. As I mentioned already, it's a bit coarse, and that, of course, we can say here that we want to the structure renderer to be smooth, but I won't click that yet. It's just then would look smoother than it is. Here again, clipping into the x-axis, maybe the z-axis, the vertical axis a bit. Down, then what we have here here you can see what I mentioned was the staircase effect. If I zoom in a bit more, that's actually want to have a look at that, but not on the 3D, but on the 2D. Let's go here to the vertical. That's the z-axis. Oh, I clipped the structure, didn't I? So and then we go down there. So now zoom in a bit. So we can see that one here. And now if I that close, I can here also enter the gridding and can see the regular grid. That just won't make sense. If I zoom out, you would just see gray scale. But if I zoom in again, you can see here in this case, there's just one voxel layer. As you asked previously, maybe this one here is a bit too coarse sampled. So with 272 micrometers, you just have one voxel thickness in here, and also on the tips here to have a flow velocity through that part here. Well, there's just not a bit too few voxels. So for a real relation done higher grid sampling, but for this one here, that's fine. So now we are already in the vertical. We have a lot of structures here. So maybe, do I need to reassign that? I probably don't. Let's just assign. Well, we can in the presentation I've reassigned everything to one structure, but we can also say, okay, this is all solid. These are all solids here, except our one here use oil. Let's make it thick, and we have our filter media. This is actually a porous media with the same fluid inside. We don't need the solid densities. We don't have any mechanical simulation here, so we just neglect that. That's all solid, everything out there. So go here to the permeability and have to enter that. What's that, 10 to the power minus 11, isn't it? What was 10 e minus 11? No? Oops. That would be 10 to the power minus 10. So 10 to the power minus 11. And then it assigns everything. And we have here our filter medium. I can also make the label there. You can do that later. But so here, the label was then filter. So run on that. And we have now our filter. That's the ID 10. We will need that later on. And now we have to specify inflow and outflow. Let's go up to the structure here. That's a bit down. So here we are. In this case, I will specify this one here. Oops, where is it? Select voxels. I need. I've actually painted a voxel. Just want to select that. Select that voxel. I'll say, okay, I want to have this plane filled out with a new material, which then would be the 12. Material information was the outflow, isn't it? And I'll run that. Oh, now I have to. Now I select the other ones. 3, 4, 5, 6, 7, 8. And fill that with this 13. This is then my inflow. And I'll run that. So now, let's see, going back to 3D. Yeah, I've marked those. And now we have one inflow plane, several inflow plane, one outflow plane. It's just the blue was the last time it was the other one around, isn't it? Okay, so now we can have a look at well, maybe it's better to have one color, isn't it? That's a bit crowded. So we put everything to 1, run. Reassign materiality, the 3. I think that was not intended to have it done so often, isn't it? 4. Just have to keep in mind that I don't reassign the 10. That's a bit. So reassign material, then the 6. Run. Reassign 7. Reassign 8. Then the 9. And reassign the 11. Not that. Yeah, so, okay. Now maybe let's say, okay, that's not very nice. Make the casing some light gray. Solid is fine. Three. I think I forgot a 3, isn't it? Here. Let's make this one. That is yellow. I don't think so. So, okay. So now what we have assigned here is, okay, here it's already as oil stated, probably because you did remember that I've done that sometime. That would not be the case. We could change it here. And the considered material tab. We'll also rename that. That's the casing. So, and let's run that. So that's already our structure. I can file through that a bit again. Now, we can actually do the following. I will make that here and there, and then invert that. We can have a look inside. So maybe that's so. No, make it the other way around. So that is our filter. Maybe this one and this one here. So okay, and now we want to run a flow simulation on that. So use filterdict, complete filter flow experiment. And edit. As I mentioned, one can change the material settings here. We need here the fluid properties and the permeability of our porous medium. We choose fast flow to get faster results. Pressure drop, I think I would use the flow rate here, isn't it? What was it in my example? 10 liter per minute. 10 liter per minute. Okay, in that it has not. Why isn't the? That is interesting. That is interesting. Well, actually, I specified the the other way around. Let's see if this changes anything. The 13, mapping that to the 11. Doesn't change anything in the picture. Let's see. This now finds 2. This here is still stated overlap now. That was not the intended outcome. Actually, it detects inflow and outflow if you label it correctly. Now, of course, I mapped it to another one, so couldn't find that anymore. And that here is now was the inflow. So, okay, inflow, run that. Now let's go to edit again. To the parameter settings here. And now it found 2. Could someone make a note, please? There seems to be an enumeration issue. So that's here the 10 liter per second. It had found the inflow plane and the outflow plane, actually the inflow planes and the outflow plane. Boundary condition, yeah, no, slip is fine. Actually, I think we haven't looked at any gaps, isn't it? But let's omit that for the moment. Yeah, so, okay. Oh, no, I don't know why my mouse is jumping. Well, equations, if you are interested in that, where the references for these flow equations are, I press OK, and then I just click Run here. I'm not logged in any cloud or job queue system, so I have to do it. Active process. Something is wrong here. Let's open the. Oh, that's the large one. In porous casing. Something. That should not be the K. Yeah. The point here is that this one here, okay, this one here has a slice 400. So there is actually one slice above that. And at the moment it assumes the, well, actually all but the inflow has two directions to go from. And at the moment it will take the shortest way. So I have to crop the upper layer. Crop, then set, just going one down there. Run. So now it's working. So let's see how long that takes. So okay. So in the meantime, I promised you to look at the, no, I cannot do that. That should be faster. So what I also wanted to show you then is the scripting. I just can cancel that. I don't need that. Okay. So as you can see, the importing the CAD data, analyzing a bit on the structure, and setting up the flow simulation was quite fast. The longest part here is obviously to run the simulation. Yeah, I cancel that. That's fine. So now what we wanted to do here is execute macro, and here inside we have our cylindrical pleat analysis. That's the one you've seen here with the UI. As I promised, the run flow simulation is there too. Now what you can do here is to say here, well, pleat material is wrong here. Of course, that's the 10. And then let's say replace it by, I don't know, 20 pleats. Before I do that, I click edit here because every script you can open. And I have to find it first. Where is it? Oh, there it is. So where's my mouse? Oh, there it is. So, okay. So I click run on that. Yeah. So, and we'll do run a bit. As I promised, some about the automation. Well, of course, you can also say running the complete module also in the cloud for several parameters. What I've shown you here is that you can already conceal a lot of parameters behind a script. Because here, for example, I used here the specifying variables, but I can make this, I think it's Alt-O, isn't it? Fold all. We have our flow simulation. Here's a load file, reassign, run flow simulation, and inside there, where's the flow simulation? Run flow, that's probably somewhere up there. Exactly. Yeah, run flow simulation. That's just one command line. And then we have the parameters up there. The parameters which we do not use are hidden behind that. So there's the complete experiment setup, the solver data. we actually changed the result file name. But beyond that, we only changed those variables which we actually change. Well, actually, in this case, it's just the material properties. And then we run the flow simulation and get a result of this run flow back. That's then, where is it? There, run flow. And we get our pressure drop extracted from programmatically from our result file. So actually, we are hiding the simulation behind our script, behind our GeoApp, behind our small user interface, where only those values which we want to change are actually changed there. Before that, there is a bit of lengthy stuff going on here. Here was this printer with a pleat detector, which you've seen on the screen. For that, it has to go through, well, it actually just goes through the slices and checks where the pleat is, where the material is present. The same is true for counting the bounding box, just going slice-wise through that and counting minimum and maximum values in any direction. And by doing that, we have analyzed the tool, and let's see, we have a result here. Let's file through that. And here we can see we have replaced our pleat by, well, a pleat with 20 counts. Of course, the sampling here is quite coarse. That's also why some details, like it's closer to the inner boundary in this part than on that. The center point is determined, but with a 272 micrometer sampling, maybe a bit too coarse. Let's drop the maybe. So, okay. So then, as you can see here, we have done that. And then, of course, we can also click here on the run simulation part. Okay, now it starts with the structure we have included. So don't want to do that here. Let's have a look on the, what is that? That's the complete, that was the complete filter with 1078 voxels, so 100 micrometer sampling. And in that, let's see, where's my result file? Oh, that's here, okay. Let's see if I can find that. So the script was then completed. That was that. Let's see, do I have a result file on that? Yeah. No, that's not that. Complete filter flow. Oh, okay. I've not put it on there. Exactly. Here's one result I downloaded from the cloud. Was the one with 0.59 radius and 71 pleats. We have a result file there. We'll just open the complete flow result. Load the structure on that. Yeah, you can see our complete filter with 71 pleats. And I can open the flow visualization. In this case, I will only load the absolute values because I don't want to have it decompressed. It will then load faster. Because I think we have only a few minutes left to get on time to the upstairs again. And I think we have a Q&A, isn't it? Left. Is there anything on the Q&A there? While this is loading. So, okay. While this is loading, well, my laptop isn't the strongest one today. Are there any questions on this workflow? Okay. So set to invisible. Yeah, the structure, I don't want to see that. And now we have here our flow. If you said this is quite coarse because it's a not decompressed file. So at the moment, the adaptive gridding of our flow solver is still visible. We can see the larger areas where not much is happening over there, and it's getting finer if it goes to the openings there. That's actually the velocity field. Let's see, a pressure field. Okay. Oh, that's the other way. That's the inverse one. Yeah. Okay. Good. Yeah. So much for that. You can see here that we have. Don't be intimidated about the lengthy script on that. You can see that you can do anything or anything in automation from the script. You can run geodig commands like reassign and load files. You can access the volume fields, as I mentioned, to get here, for example, what is it? The setting of the new pleat into the old one. That's actually the loading file was to load the initial structure, then removing actually the old filter and setting the new filter, and that's just those few lines here. And then we have already done that. We have a UI which we can use to validate. I can also show you that. Macro run script. What I mentioned here was we had those parameters here. They were just click here on the vary. We can do a complete parameter study by entering it into the UI here. Thank you for your attention. I want to wait a second. Where is it? There it is. Let's make it that way. So there, if you want to book a session with our filtration expert, you can scan this QR code, and then I want to thank you for your attention and your time today, and have a good remaining afternoon, and we'll see each other. Well, those on site, we'll see each other later at the dinner, isn't it? Okay. Thank you very much.